almost till the end. This is the last section that we're doing for gases. Just a few more slides to go through. What is STP? STP stands for Standard Temperature and Pressure. STP is important when you're doing laws of gases, whether they're physics or chemistry or biology, as we have learned from Boyle's and Charles' law, that both temperature and pressure affects the volume of a gas. So in order to, and for an experiment to be repeated, it has to be confirmed that you use the same kind of laws or same conditions are applied, whether an experiment is repeated from example in Milan, Italy to Australia, or to Bisbee, Sierra Vista, or in New York. The standard temperature is always 0 degrees Celsius or 273 Kelvin, and the standard pressure is considered to be 1 atmosphere or 760 millimeters mercury. What is molar volume? Molar volume is the volume of 1 mole of a gas. 1 mole, which is again a mole of a gas, if you remember from the previous lecture we did. For example, if I was to take mole of N2, what would be my mole of a gas? That is the quantity of particles would be, of course, the Avogadro's number, but the gram of this mole would be, recall, nitrogen is 14 times 2, which would be 28 grams. That would be that's how much of the mass we're taking. Now, a mole of that gas, of any gas, whether it's a nitrogen or oxygen or chlorine or hydrogen, will always occupy the same molar volume, that is 22.4 liters. Remember, gases occupy the container in which it's kept, so the volume of the gas would always be the same. However, you can relate whether the pressure would be the same or not. So keeping the molar volume and the different concepts we did, let's look at the last law of this section, and that is called as the Dalton's law. Dalton's law is probably the easiest to understand. The Dalton law says that if you have a mixture of gases, for example, if you have gas A, gas B, gas C, and gas D, the total pressure of all of these gases, or the total pressure exerted, would be the sum of pressure of A, pressure of B, plus pressure of C, plus pressure of D. So we, for example, are living in this sea of gases, and the pressure that's exerted is the total pressure of all gas particles. So pretty much in this experiment, there's no multiplication and division. All you're doing is adding up all the pressures. However, you got to pay attention to one little detail that I'll show you in the next slide. So the total pressure, remember, is going to be the total is going to be the partial pressure of each. So that's why it's called as the law of partial pressure, because it adds up all the pressures of each gases. I'm gonna go back over here. Okay. Yeah, the difference that I wanted to tell you about in here when you're adding up is just like you can't add apples and oranges. So if the pressure of one gas is given to you, for example, in torr, and the pressure of another gas B is given to you in millimeters mercury, and we want to know the total pressure in millimeters mercury. Now you cannot add the torr unit and the millimeters together. So you can't say if this is 50 torr and this is 500 millimeters that the total pressure is 550. You would have to convert your torr to definitely millimeters mercury. And again, for this part, you will use dimensional analysis. The setup would be, again, I'm going to show it to you over here. 50 torr needs to be converted. Well, actually, it is 1:1, right? So 1 torr equals 1 millimeters mercury. I know you're saying it's the same, so why do we have to do it? But you would have to set up the whole thing to then show that you have converted that to 50 millimeters mercury. Now, for example, let me erase this, and instead of 50 torr, let's just say that this was 5 atmosphere. So what would you do then? You would have to then, let's get back, get rid of a little bit of information over here, And this is the original problem that I wanted to give you. Anyway, so you have 50 atmosphere. You would have to convert 1 atmosphere equals 760 millimeters mercury. So you would convert 50 times 760 millimeters and then add up the 500 millimeters to get your total pressure. So pay attention when you get to the partial pressure or the Dalton's law, because in these you would have to make sure that your units are of the same before you do the addition. Scuba diving is another example. This is just an interesting fact. When a scuba diver dives, it increases pressure, which causes nitrogen to dissolve in blood. Now, if the diver rises too fast, the dissolved nitrogen forms bubbles in blood, and this is called as the bends. Helium does not dissolve in blood, and that's why it is mixed with oxygen to prepare breathing and mixtures for deep descents. Another scenario of the gases is the gases we breathe contain nitrogen and oxygen and small amount of other gases. Oxygen enters while carbon dioxide is released. And the tissues do absorb oxygen and release carbon dioxide. So oxygen flows into tissues because the partial pressure of oxygen is higher in blood and lower in tissues. However, carbon dioxide will flow out of the tissues because the partial pressure of carbon dioxide is higher in tissues, because that's where after respiration it's being given off, and it'll be lower in the blood. So these two are just examples of different scenarios of everyday life where you're applying the different gas laws. So this concludes your section with gases. Again, please make sure you do your weekly assignments on web study, and also keep in mind that you should practice a lot of these mathematical problems. I've tried to do a couple in here, but that's still not enough. You may have to do more practice with some of these problems on the word problems to be able to relate to all the mathematical expressions.